Remember that a vector is characterized by a magnitude and a direction. A vector can start anywhere, might as well start at the origin, but it's characterized by this direction, we'll call it alpha. Sometimes that angle is called the argument, and it's characterized by the magnitude. Often we denote that by absolute value signs. So if this is v, now somehow that magnitude is fundamentally related to how far it moves you in the x direction. Sometimes people call that v sub x, and how far it moves you in the y direction. Sometimes people call that v sub y for obvious reasons. That's a right triangle, so somehow these sides are related by the Pythagorean theorem. Remember that vx squared plus vy squared is equal to this magnitude squared. So the magnitude itself is equal to the square root of those pieces. If you have the magnitude, if you have the x component direction and the y component direction, you can get the magnitude. Similarly, if I'm looking for the argument of the angle, okay, if I'm looking for that argument, well, so think about how if you had that, how it would be related to these two sides. Well, the tangent of alpha is vy over vx, so tan inverse of vy over vx would give you that argument. Now, I should put in the caveat that that works in quadrant 1 and 4, right? Because tan inverse assumes that an angle is in quadrant 1 or 4. If you're in the other quadrants, you're going to have to sort of use your noggin about how to take the angle it gives you, assuming you're in these quadrants, to put it in the quadrant the vector is actually in. So let's think about that for an actual problem. Notice in this particular problem, v moves us right 4 and up 6. You could actually write that. That's the component form, and so the absolute value or the magnitude of that would be the square root of 4 squared plus 6 squared. And if you punch that in, square root of 4 squared plus 6 squared is going to give you something that is approximately 7.2. Okay? If you're looking for the argument here, that's going to be tan inverse of 6 over 4, which will give us approximately 56.3 degrees. Seems reasonable, first quadrant, all is well. Now you can go the other direction as well. That's for going from knowing the components to knowing the argument and the magnitude. But of course, if I knew the direction, or the angle, or the argument, and I knew the magnitude, how would I get to these two sides? Well, think about this. How is the adjacent side related to the hypotenuse and the angle? Well, sine of alpha equals the adjacent over the hypotenuse. So if you're looking for v itself, the x-coordinate, vx, is going to be equal to the magnitude of v times cosine of alpha, right? Because cosine of alpha is the x direction over magnitude of v. And the y direction, similarly, is related by sine. It's the magnitude of v times sine alpha. Think about that. So those are the two pieces, if you know this, that you can find the x component and the y component. So let's imagine that I have this problem down here. Okay, I know the magnitude, I want to know the argument, and I know the argument, I want to know the vector itself. So v equals 13 cosine of 124, 13 sine 124. Okay, and notice the nice thing about using sine and cosine themselves instead of their inverses is that there's no limit, there's no assumption about which quadrant I'm in. So 124, of course, is in that second quadrant, but all is well. If that's 13, I'm going to get a negative number for x, a positive number for y, and all will be hunky-dory. Let's see how that works. So 13 cosine 124 gives me negative 7.3, just like I was sort of expecting to get a negative. Then 13 sine of 124 gives me a positive 10.8. And there we go.